Professor Wei, your hand.
Yeah. Okay.
Yeah?
Just,
Oh, please. Oh, thank you. I see your. I see
you
your.
see my screen?
No, I
Yes.
don't see. Now I see your presentation.
Yeah. You see the presentation? Yeah.
So we have to start without any rest. Without any rest, we will rest. So I propose now to our audience to concentrate and to hear, to listen very, I guess, interesting talk of Professor Wei. So
Okay.
please, Professor Wei.
Okay. First of all, I want to thank the organizers, especially Professor Bahong, for the invitation to give lectures on this for singularities for youth, for young people. And Professor Fahong gave a very nice lecture on singularity for semi-linear elliptical problems. In fact, when I say the Severin was my teacher in Minnesota, so it's really nice to see that all this started with the Severin. So today, what I'm going to talk about are singularities in semi-linear parabolic equations. So first of all, I will give an overview of the blowup for the Fujita equation. So if there's any problem, please let me know because I could not see the audience. Sorry. And then so my main aim for these lectures is to introduce the parabolic green method. And there are two cases which I will discuss. And maybe today I will discuss the simple case, which is the L2 case. And where the P is the critical exponent, we do dimension 5 and 6. And tomorrow I will do the non-L2 case with the dimension 3 and 4, when P is the critical. Okay, so there are three references for this parabolic green method. And the L2 case, you can look at the Kalman, Cardazza, and the Pino Monica. For the non-L2 case, you can look at Juan Davina, Manuel de Pino, and myself in 2020. And also this survey paper, lecture notes on the parabolic green method is on my website. And this is my the website for these lectures. So this is about 100 pages. Okay, so first of all, let me give an overview of the blowup for nonlinear heat equation. So we'll start with the semi-linear heat equation. So this is the same equation like in Professor Fahong's talk, but we put a UT. So we have an actual dimension, which is the time. And so for this initial condition is well known, this local well positioning, this is standard parabolic theory. And what we're interested in the case when the solution become unbounded, in the sense that the limit soup, as t goes to some finite time t, it becomes infinity. And we know that this happens. This started from 1996 by Fujita, and this very nice book by Quinton and Supernet, and this is a Fujita exponent as well. So there are two types of blowup which we are going to classify. For this equation, if the blowup looks like ODE, so in this problem we have three terms: UT, Laplace, and U to the power P. Now, if the blowup, we have a blowup. If the blowup looks as ODE, means you drop the Laplace equation, and then you have this type of ODE blowup. So this, so if you have this type of ODE blowup, we call type 1. So type 1 means the L infinity norm is bounded by the ODE blowup, and by by simple parabolic theory, this is also bounded from below. So in other words, type 1 blob is like the solution blobs like ODE. Otherwise, if it's not type 2, type 1, then it's called type 2. So it means this means you cannot bound the area infinity by this singularity. And if T is infinity, then this is blob at the infinity. And so first I will discuss some results, okay, on this problem. I will give you a survey on the results on this problem. And then later I will concentrate on the particular case where P is critical exponent, and I will discuss the parabolic Green method. Okay. So let me first discuss some results on classification of blobs. So when P is less than this number, which is n plus 2 over n minus 2, and this is so-called critical exponent, and we know that all blobs are type 1. Okay, so all blobs are controlled by ODE. Okay, the blobs are controlled by ODE, and this is a classical result by Geiger-Kohn, 1987, for positive solutions, and Geiger and Machu and Sasayama for sign change solution. So when P is subcritical, you have a very good control of the blob. All blobs are type 1. And in fact, Mayer and Zag gave a complete self-similar isometric behavior of the type 1 blob solutions. Now, when P is critical, when n plus 2 over n minus 2, this is called energy critical case. And this is more difficult. So in the energy critical case, the first result was a formal result by Fenipas and Herrera and Velasquez, and they showed that all blobs are type 1 for positive readily decreasing solutions. So if you consider functions as readily decreasing, but positive. And later, Collard and Mayer and Rafa, they proved that all blobs are also type 1 in dimensions n greater than 7, provided your initial condition is close to the first Orban-Talanti bubble. So if the energy is small, in other words, if the energy is small, then all positive solutions are also type 1. Okay, are also type 1. And between 2021 and 2024, with Kelly Wang, we have a paper which is of 200. We give a complete classification for n greater than 7 and the P equals n plus 112 for any initial condition, any L infinity initial condition, or if it's readily symmetric, n greater than 5. And we show that all finite time blobs are type 1. So even in the critical case, all blobs are type 1, positive solutions. Okay, and so now the question is, are there type 2 blobs? So all these results are classification blobs to type 1, are the type 2 blobs, and there are plenty of type 2 blobs. So the first result is Fenipas, Herrera, and Velasquez in the same paper. And this is a formal computation for dimension n to 6, and when P is a critical exponent. And they formally construct the type 2 blob. And the first rigorous result due to Schur in the radio case for n is 4 and the P equals 3. This is a critical exponent. And your blob, the blob is like a log square over T minus T. And the proof is by Rafa and Rodensky, this modulation approach. And later with Depino and Monica, and if so, we give a new proof, but for non-radio data and multiple bubbles. And we have the same in the outer green. And this is called the inner outer green approach, and which I'm going to discuss this method based on this paper. Okay, so this is dimension 4 and the dimension this is dimension 4. For dimension 5, and there are also multiple blobber type 2 blobs, and the blob rate is t minus t to the minus 3. And for dimension 6, Harada proof the type 2 blob in the video case, and the blob rate is first strange order. Okay, and for dimension 3, you can have also non-radial blobs and radial or non-radial blobs for any blob rate t minus t to minus k. K as long as k is an integer. Okay, so this is the critical case, type 2 blob. For the non-critical case, for the supercritical case, there are many results. The first result is by Gerardo and Velasquez. And when P greater than the Josephson-Langley exponent, so there's another exponent which is much bigger than the Schrodinger exponent. It's called Josephson-Langley exponent. If P is greater than this Josephson-Langley exponent, you have type 2 blob. And when P greater than the Josephson-Langley exponent, and this is a radial case. For the non-radial case, this was proved by Collot, but he assumed that P is odd integer or odd integer. Now, if P is not only bigger than the Josephson-Langley exponent at n, but bigger than Josephson-Langley at n minus 1, it's possible to also have blobs which are anisotropic. Okay, this is an anisotropic blob. This is Collot, Mayer, and Rafa. Now, when P is between the critical exponent and the Josephson-Langley exponent, and this is called Montana-Mayer, and they show that basically you don't have type 2 blob, no type 2 blob in the radial symmetrical case. However, there are type 2 blobs in this regime in the non-radial case. So in the non-radial case, you can have type 2 blob, but in the radial case, in this regime, you don't have type 2 blob. There are many different kinds of type 2 blob in this non-radial case, in this regime. For example, you can also have type 2 blob with a ring for p equals 3 and n going to 5 and less than to 8. So, and the loss of type 2 blobs, there's loss of, but a complete classification of type 2 blob is unknown when p greater than n plus 2 over n minus 2. Okay, so this is a summary of the results on type 1 and type 2 blob. So basically, below the critical exponent, you don't have type 2. Your all blobs are type 1, and greater or equal to the critical exponent, you have type 2 blob. You start to have type 2 blob. Okay, and when P equals the critical exponent, you don't have type 2 blob for possible solutions. So, so how do we prove construct a type 2 blob? And this is the main aim of my lecture, is to introduce you the method of constructing type 2 blob for parabolic problem. So in the rest of the lectures, I will introduce the so-called inner-outer parabolic Green method. So this method is to extend the inner-outer Green method, or we call the infinite dimensional reduction method, for the elliptic case to parabolic case. Now this inner-outer Green scheme was first developed by Manuel de Pino, Michael Krasik, and myself in 2011 paper. And in that paper, using this inner green, outer green scheme, we gave a counterexample to the de Jouvre conjecture for the Arnold-Kahn equation for dimension n greater than 9. And later, with Manuel de Pino and also Juan Davila, we extend this inner outer green to the parabolic case. Okay, so what is in the outer green, and how do we use the inner outer green to construct type 2 block? Okay, so the inner outer green scheme for individual problem is very easy. The idea is we have a singularity. It's like you have when you see a cancer in some patient. So how do we see the cancer? What you do is you zoom in the cancer region, zoom in the singularity region, okay? And you look at this, of course, usually this singularity region is very small. You zoom in the singularity region and you decompose the whole nonlinear problem into two problems. One is the inner problem, which is near the singularity. And in this part, you solve the problem capturing the essential geometric information of the interface. But the outer problem is solved in the whole space. You sum up all the global and external effects. So the key elements in the individual green is the Friedholm alternative and the modular space theory for elliptic operators. Okay, so in the parabolic case, we do the same. The idea is to zoom in the singularity and decompose the whole nonlinear parabolic problem into two problems: the inner problem and the outer problem. Okay, now the key element in the green is to have a good theory for the linearized parabolic operator. So now I will introduce this green method in two cases. The first is the easy case, which we will do today. I call the L2 case. Now, next time, tomorrow, I will do the non-L2 case, which is the more difficult case. So I will start with this Fujita problem with the critical exponent. It's very easy. The ut equals Laplace u plus u to the critical exponent. And I will consider two cases, n greater than 5 and n equals 3, 4. Okay. Tomorrow I will do 3 and 4. But today I will do dimension 5. Okay, I will look at dimension 5. Okay, now remember we have the existence of type 2 block in dimension 3, 4, 5, 6. Okay, and so today I want to show you how you come up with these dimensions. Okay, so the building block for the problem is very simple. Is the Orban-Ternandy bubble. So you take Laplace u plus u to the m plus 2 over m minus 2, or possible solutions, and so all solutions can be classified. We know that is called a Ternandy bubble, and they're given like lambda over 1 plus lambda square x minus z square and to some power m minus 2 over m minus 2. Okay, and with scale you can, so it's all generated by one function. So you have lambda as a parameter and z as another parameter, which is the translation. So basically you have m plus 1 parameters. Okay, so if I linearize around this problem, we know about this profile, we know all the linearized solution. So here P is the m plus 2 over minus 2. And for this linearized problem, we know that there's a principal eigenvalue which is unstable, and the corresponding principal eigenfunction is exponential decay. And then we have m plus 1, 0 is the second eigenvalue, which has a multiplicity m plus 1, and they're all translations and also scalings. And The rest of the eigenvalues are stable ones, okay? So now let me now classify why I call alto case, why I call a non-alto case. So if you look at the zero eigenvalue, the eigenfunctions, and these zero eigenfunctions, if n greater than 5, they're all in L2, okay? These eigenfunctions are in L2. Now, if n equals 3 and 4, these eigenfunctions are not L2. So I call the non-L2 case. So today I will only discuss the L2 case. So I will take the simplest example, which is dimension n equals 5, and the P is the critical solve is 7/3. So the main result I'm going to present, I hope after this lecture, you at least you learn something. That is the Green method. So the result is the following. So you take n equals 5 and P equals 7/3, and for any given point, and for any small time t, capital T, and you can construct a initial condition such to the Fujita problem so that it blows up exactly at the place Q, and with this blow-up rate. The blow-up rate is 1/t minus t cubed. Okay, so and lambda is t minus t squared, but L infinity norm is 1/t minus t cubed. And furthermore, you know exactly the blow-up is stable. In other words, except for one dimension, all the initial condition all will produce blow-up. So the blow-up is one coordination one stable. Okay, and in this in this lecture, I will just take Q equals 0, and I will do the simple case, read the symmetric case. Okay. Okay. So let me first do the formal computation. I want to convince you that there is a type 2 blow-up. Okay, and then I will say how we can rigorously prove. So it's always you do some preliminary computation and you found out there may be a type 2 blow-up, and then you try to use the Green method to construct this to rigorously prove this. Okay, so what we do? We take this Waban-Talanti solution with this scaling parameter lambda, and you may have some some error, okay? Okay, some initial condition come from the initial condition. So we take this answers. How do we choose this error? We choose this error so that it satisfies is a solution to the heat equation with some initial condition. Okay, with some initial condition. So the initial data is u of lambda 0 plus c0. Okay, so this is our answers. So let's now plug into the operator and do computation. So our operator, Fujita operator, is lambda 0 plus u to the power p is the critical solve minus ut. And so you plug in the very simple computation. You say you have two error terms come in. One is from the process 0, because you put some noise, process 0. And another one is ut, because u is a stationary solution. So, and the lambda you don't know, lambda of t you don't know. So what you get when you rescale this error, you're going to get the error is process 0 lambda y, and then this error you can compute out is nothing but the scaling parameter. Okay, it's the kernel correspond to scaling parameter. This is a very simple computation. Okay, so this is error, and so you from the Parabolic theory, we know that if you want to solve, because you have a kernel, of course, you want to solve the problem with the right-hand side, you need to orthogonal to the kernel. Okay, we do the orthogonality condition. You take the orthogonality condition, okay, put this error in, and you plug in the orthogonality condition, and what you get is this ODE for lambda. And basically, this OD phenomena says its number of prime must be some constant times for set 0 of 0, because your this is your noise from the outside, lambda to the power n minus 4 over 2. So if we look for finite time block, plug this one in, you found n must be less than 6, otherwise this cannot happen. And also percent 0 must be 0. So what does this mean? Okay, so this means you cannot have a positive block, type 2 block. Your outer problem, right? So after you take away the bubble, your outer problem must be positive, must be negative. So in other words, your solution, if you have type 2 problem, it must be sign changing. So all the solutions that were announced from dimension 3, 4, 5, 6, they're all sign changing solutions. Because you see, just from this simple computation, you cannot have positive type 2 block for the critical problem, critical exponent. And here, in this example here, the computation says n must be less than 6. But what about n equals 6? So n equals 6. Now remember, in this computation here, I take the solution for the heat equation, for the linear heat equation. So for n equals 6, you cannot do this anymore. What you need to do is you need to put a type 1 solution on the top of a type 2 solution. So the type 1, your outer problem is a type 1. The type 1 block, you put a type 1 block on the top of on the top of type 1, you have a type 2. So the 6 is a special. But anyway, this simple computation says the type 2 only block only can happen in dimension 3, 4, 5, 6. Okay. So let's try to make this rigorous. Make this simple computation rigorous, because this is a formal computation. Right? And also we need to find the exact beta, okay, the proper rate. Okay. So how to do this? As I said, that we use this parabolic green method. So the key element in the parabolic green is freedom and modular space. But for parabolic problem, we don't have freedom theory. Okay, there's no freedom alternative for parabolic problems. So what do we do? How do we construct a good freedom theory for the parabolic problem? Okay, and so this parabolic green method is contained in this paper, and you can download from our website, which is a full. The published version only 77 pages, but the full paper is 177 pages. It contains all details of this parabolic green method. Okay, so what is the idea of the parabolic green, and what is the takeaway? Okay, so the idea is the following. So we take this parabolic problem, Fujita ut equals Laplace u. So they forget a u here. Laplace u plus u to the power p. So we divided the problem into 3 regimes. Okay. So when x is very close to your singularity, so when x is much smaller than square root t minus t, then ut is much smaller than Laplace u. So in this region, I can just drop ut. The problem is almost elliptic. Okay, so almost elliptic. So this is the elliptic region. Now, if x is like a square root of t minus t, then this is a parabolic region. Okay, this is a parabolic region. Now, if x is much bigger than square root of t minus t, then this is the OD region. So we have elliptic, parabolic, and OD, and we have to say how to do the grouping of these 3 regimes. Okay, how to how to the growing of this three regime. Okay, so let me now introduce the parabolic inner outer growing. So we take this is our we need to solve is ut minus Laplace minus u to the p equals 0. So we write this as minus ut plus Laplace u plus u to the p equals 0. In the main order, we want to find a solution of this form. So let's assume that Xi equals 0. Okay, so the general strategy is very simple. So we'll construct a good answers. Okay, depends on 2 parameters, lambda and Xi. And then you construct a general solution by linearization. And this phi is small compared to U0. And so the solution for the linearized problem is also very simple. This is a linearized the parabolic problem, and this is your error. This is a nonlinear. Okay, this is a nonlinear term. Okay, so everything is just undergraduate calculus. Nothing new here. No. Okay. Okay, so the crucial part of this inner outer growing is to decompose your solution. So this is the Orban-Tananti bubble. This is a solution you want to construct. And you decompose your problem into 2 parts. One part is phi, which is the inner problem. Another part is psi, which is the outer problem. Okay, so now you have you start with one problem, but now you decompose this problem into 2 problems. The inner problem and the outer problem. You see that in the inner problem, I use the inner variable. In the outer problem, I use the original variable. Okay, so phi solves the inner problem. So for phi, I only solve very close to the singularity. Okay, and the psi solves the outer problem, and eta is some sort of a cutoff function. So both equations, this form a nonlinear parabolic system. Okay, so how do we formulate in this as a inner outer growing? Okay, how do you decompose one problem into 2 problems? So let's fix a point, and we choose an initial condition so that at this point that so you start with a heat equation, and at this place your solution is negative. Okay, so we write our problem as u plus z star. Okay, this is the noise, and the plus phi, and the phi is the inner and the outer. Okay, this is inner and the outer. And you plug into this, you've computed the new error, compute the error, and so you have this. Now, the important thing, you have to group the error terms, and some of the error terms you put into the inner part, and some of the terms you put into the outer part. Okay, and so this is the inner outer growing. So you have this inner problem and the outer problem. Okay, and the outer problem. Okay, so just to simplify, because there are lots of terms. Okay, in many computations, there are like 20 more terms. So let me just to simplify the presentation. Let me just think out the most important terms that from the inner outer growing. So what is the inner problem? So inner problem, you linearize the Orban-Tananti bubble. Okay, and for the cutoff, for the error, you do cut off. You cut the error in the inner part, and then there's one term which comes from the outer, which is p u0 p minus 1 times psi. Psi is the outer problem, and this is a quadratic term. Okay, and so this is the outer problem into the inner problem is through this linear term. Now, how does the inner problem enter into the outer? So the outer problem you solve you solve basically a parabolic equation, but you cut your Schrodinger potential because your Schrodinger potential in some parts are not good because it does not satisfy the maximum principle. So you cut your Schrodinger potential, and so you have an error, which is you also cut the error. But then you have these cutoff functions. These cutoff functions come from the outer problem, from the inner problem. So the outer to inner to outer is through this cutoff function. Okay, this is 2 times gradient eta, gradient phi, plus 5 times Laplace eta. Okay, so you solve this problem in the whole space, but you solve this inner problem just in the very, very small region, which is very close to the singularity. Now the question is, you have to choose this R. Where do we do the cutoff? Okay, so let me repeat. The outer enter into the inner through this linear function. The inner enter into the outer through the cutoff. Okay, so this is the basic idea. Okay, so the question is to choose a suitable radius R so that the inner and the outer problem somehow can decouple. Okay, so we have to choose R. Of course, your R times lambda should be much less than square root T minus C because square root T minus C is the self-similar regime, is the regime, the parabolic part. So you should stay, for the inner problem, you should stay inside the elliptical regime. But if R is large, then the outer problem is better because you are multiplied by the cutoff. The cutoff give you more regularity. But then the estimate for the inner problem get worse. So there's a suitable range of suitable Bayesian, okay, force. You have to choose a good R. And how we choose this R is very important in the non-L2 case. But in the L2 case, you can just simply choose R to be fixed but not large enough. Okay, but for the non-L2 case, you have to really choose a good R. Okay. So today I will just choose an R which is fixed but large enough. Okay, so for the inner problem, we do this inner variable. We take we scale x and also we scale the lambda. And then the urban tonality ansatz becomes this. So the inner problem is very simple. Is phi tau equals Laplace phi plus pu p minus 1 phi plus some other terms, error terms. Okay. So the inner to outer is just the mentioned before. Outer to inner is the linear term. The inner to outer is the cutoff function. Now, a very important observation is you see that the inner problem, the effect from the inner to the outer is only through the boundary. So you may have a function which is very large inside, but if it decays near the boundary, near the place where you do cut off, then this time will be small. And this is a very important observation. The solution we get are actually very big inside. However, it decays near the boundary. Okay, so for the going to work, we need to find an inner solution which has a fast spatial decay and fast time decay. All right, so this is the model problem we need to solve. We have a linear parabolic problem. Okay, this is a linear operator, linearized operator, and plus some error. Okay, and we need to, we know this error has spatial decay and time decay. Okay, and now in the initial case, if this equals 0, and you can use freedom theory. The freedom theory says as long as your edge is orthogonal to the kernel, then you're okay. But for the parabolic problem, we don't have this. So, and this we don't have the freedom theory, alternative, okay. On the other hand, the parabolic is better than the infinite in the sense that your solution always exists, okay. The problem is you need to choose a good initial condition so that your solution has good behavior. But the solution always exists. And so the problem is to find a fast decay solution in both space and time. Okay, now another difficulty, another nonsense here is that this problem is unstable, right? There's an unstable eigenvalue, okay? And so we have to get rid of this unstable eigenvalue instability, okay? So the question is, how to find a solution that's fast decay in both spatial and time variable, but inside the self-similar variable, which is y less equal to much less than the square root of tau. Okay, so in different cases you can do this by freedom theory, but here we don't have a freedom theory, and and also we have the instability, but we can get rid of the instability by choosing a good initial condition. So we can choose some good initial condition. We can get rid of the instability. Okay, and this gives us a coordination one instability of the bubble. Okay, so this is the linear theory that we need. Okay, so this is the main linear theory. So we take this linearized parabolic problem and plus h, and we want to solve the problem for y less than 2r. R is just a fixed large number, and we assume the right-hand side is orthogonal to all the kernels, okay, 1 to n plus 1, okay, and we want to choose a good initial condition with some C0 times C0. Okay, so the main result we have is if H decays like this and also with the space and the time, then you can find a same solution with the same space decay and the 2 power less than the space decay, but the same time decay. So this is the main result we want to obtain. Okay. So once we have, if we have this result, then the inner outer gluing can work. And the reason is, if you have a solution from the inner problem which decays like 1 over y to sigma, then near the boundary, near the place where you cut, the solution decays. And so then the inner to outer coupling term will gain a little bit of regularity, which is r to the minus 2 sigma over 2. And this is good enough, because this regularity, the outer problem you enter in the problem will gain this regularity, and it will be little bit smaller, and so you have this loop. The whole loop works. Okay, and the outer problem satisfies the maximum principle, so you can just use the maximum principle and use to find a super solution and get a good estimate for the outer problem. Okay, so so you get you get a little bit decay for the outer problem, and then you go back into the inner problem, and you can do the inner and outer group. Okay, inner outer group, and you have also good linear theory for the outer problem. Okay, and so now we mainly need to concentrate on the inner problem. Okay, is how we solve the inner problem. Okay, so as I said, you always have a solution. Solution always exists. Now the problem is to get RPL estimates. Okay, how to get up? So, and we carry out this by blowup argument. Okay, so this is our main result. So given a mu between 0 and 1, sigma between 2 and 3. So here I'm doing the 5-dimension case, and the H is like this. Then you can find a solution to the linearized problem with the same time decay, but a little bit less than this space decay. Okay. Okay. For the non-zero, for the instability to the C0, and you can choose a little bit an ODE so that this initial condition becomes 0. Okay, but in the so that the new right hand side is also orthogonal to the unstable direction. So in other words, your new edge will be orthogonal to not the unstable eigenvalue and also the all zero eigenvalue. Okay, so this is the problem. Okay, and this gives us the coordination 1 instability. Okay. Okay, so first of all, for this problem, we can show that phi is also orthogonal to all the kernels. Okay, you just multiply by zi and times the cutoff and let the cutoff go to infinity, and you get the desired result. Okay, so now the question is, this is the main result we want to prove. How to prove this result? So we prove this result by RPL estimates, okay, by blowup. Okay, so we assume that the result is not true. So we assume that you have a sequence of functions, you have a sequence of time, and you have a sequence of values yk, so that this is 1, is order 1, okay, this equals 1, but the right hand side is very small. Okay, right hand side is very small. So we have a sequence of eigenvalue, sequence of solutions for the linear parabolic problem, and okay, and we have this. The maximum is 1, and h is small. Okay, so that's the blowup. Now, usually in this blowup, in the different case, we have the blowup. You have two kinds of blowup. Okay, two kinds of limited problem. So if your blowup point is near your singularity, okay, you have a problem near the singularity. And if a blowup is away from the singularity, then you have an isolated singularity problem. Okay, and this is the same kind of idea. Okay, for the parabolic problem. Okay, the same kind. So first of all, we do blowup. We do two cases. Now, suppose the blowup point is bounded. So your blowup is bounded, is bounded, and then you can do a shift tau to tau k plus tau, and then you do some rescaling. Okay, and what you get. Okay, and in the limit, what you get? You get a parabolic problem. Okay, very nice problem, and it is in the whole space R5. But the parabolic problem exists backward because you are taking tau k plus tau, and tau k goes to minus infinity. Right? You're looking at the backward. So you have an Asian solution to the linearized operator, and this Asian solution certifies is orthogonal to all the kernels, and including the unstable direction, and it certifies some decay. So now you need to show that this you don't have this solution. Okay, so this is the first case where when you say the blowup, and the blowup, you say the blowup, but also your time also goes to infinity. So we look back, you see an ancient solution, and this is important. And so, and because it's an ancient solution, so you cannot have this kind of behavior. So how do we exclude and linearize the parabolic ancient solution to the linearized parabolic problem? Okay? So here we do energy method, like what Professor Hong said. So what do you do? So we want to show phi infinity equals 0. So by parabolic regularity theory, we have a backward ancient solution, and it's bounded. Okay, because it's bounded, so we can do a parabolic theory, and we can get loss of decay, and then we differentiate the problem in tau, and then multiply by phi tau, and we get this this type of energy identity here. And because we have all the orthogonality condition, so this integral is greater than 0 because you are orthogonal even to the unstable eigenvalue and the 0 eigenvalue. So this is greater than 0. So we get this is greater than 0. But since we're doing the Asian solution, and this means this will be less than 0, and we get a contradiction because this is square. Okay, so this and so we have phi must be independent of time. But if independent time, then it's a solution to the integral problem. But if solution to the integral is bounded, so by non-degeneracy, we have this is linear. This is a linear combination of the kernel, but we know that phi is orthogonal to the kernel. Okay, so this is so in the first case, you see a blob, and the blob goes to the to an ancient solution of the parabolic problem. Okay, so this is the good case. So in the good case, and you have a blob, and your if yk is bounded, and your time goes to infinity. So when you look back, you see an ancient solution. Okay. Now, the second case, so if the blob point goes to infinity, so then you have a yk goes to infinity, and you have phi k, and we have this greater equal to half. Actually, is 1, but say greater equal to half. Now, in this case, we do this kind of scaling, which is a scaling corresponding to the parabolic problem. Okay, corresponding to the parabolic, and we do this scaling. Okay, let's say what is the limit. So we take a limit as a phi k goes to phi tilde, and uniformly on compact cells. Okay, and we have an Asian solution now. Okay, but it's an Asian solution to the heat equation, but with some singularity. So this is an isolated singularity, not for the Laplace equation, like in the first lecture by Professor Verhong, the isolated singularity for Laplace. Here is isolated singularity for the linear heat equation, but the Asian solution for heat equation. And so the singularity here is z to the minus sigma. So we approach it to 0, it blows up. Okay. So what we have is a removable singularity problem for Asian solution of the heat equation. So we need to show that this the only solution to this is 0. There are no solution for this one. Okay. So what do we do? So this is a linear heat equation, and with a singularity at 0, but it's an Asian solution. And this is very important because it's an Asian solution. So we can go back, and what we do is we use maximum principle. Okay, and so the idea is to use this type of functions as your Schupf solution. You always do a Schupf solution, and for some c, okay, positive, and you plug this one in, and of course you add a singularity here, which is y to the minus 3. Why this is in dimension 5, this is the fundamental solution. So you always add this and to control your solution, right? Because here we have our solution is not bounded, right? It can be unbounded, right? So okay. So you do a direct computation, you found if you use this Schiff solution, okay, and you plug in, you see that this, if I choose since our sigma is less than 3, so if we can find some C, so that this is a Schiff solution. So means this is a positive, okay, for tau between minus m and 0, where tau is large, okay. So W of y and tau plus m is a Schiff solution. And for all m, now we take m, let m go to infinity, and because my epsilon is small for any epsilon, and so we get a phi tilde equals 0, and this gives a contradiction. So okay, I give you the proof, the RPL estimate proof for the linear problem. So this is the result we want to prove, right? This is the equation we have, the linear parabolic problem, and we use the block argument, the standard, the block, the Gator's spark type of block argument. But now we adapt this to the parabolic problem, and we see there are two cases. Basically, there are two cases. One case, you have Asian solution for regular linearized parabolic problem, and you need to exclude this. So you need to exclude the Asian solution to linearize a parabolic problem, and if yk goes to infinity, and what you have is an Asian solution of the heat equation, but with a singularity, with an isolated singularity, and the isolated singularity, you see that sigma is less than 3, so that is still reasonable, because if this cannot be 3, right? So we know that for isolated singularity for the elliptical problem, if phi can be controlled by the fundamental solution, then this is removable. And this is the same type of argument for the heat equation. So if your singularity can be controlled by your fundamental solution in R5, then this is removable. But this is only true for the Asian solution. It is not true for the forward, for the entire solution. Okay, so this is true for the Asian solution. And so, and finally, so we have the inner outer Green, and then with the linear theory, we can use the shelter fixed point and formulate this problem as a fixed point problem in some suitable Barkha space, and the problem can be solved. So so this is the so what I did today is to prove, to give you a lecture, on this for the dimension 5, okay, for dimension type 2 block, for dimension 5, and this is the called the L2 case, and so I introduce what is called in the outer Green, the inner outer Green, and the parabolic, the linear theory, which is like the freedom alternative for the parabolic theory. And this is the L2 case, and this is the case when you take a limit, you can take a limit, because in this case, when you take a limit, this works. On the next time, I will discuss when the case we cannot take a limit. In this case, you cannot take a limit, and then we have to see how we do the non-evident case. So I will do this next time. Okay, thank you.
So you're finished, yes? So thank you very much. Some question. Who?
Нет, микрофон только у тебя.
I would like to propose to give question.
Yeah.
It was very strong, very intensive lecture. I suppose that it yields very many interesting questions. Please.
We have
Why there are 6 solutions of C?
Let me pronounce it. Could you please explain again?
Yeah, when n equals 5, so it's very important is the Asian solution. So what do you show that for Asian solution, you should be independent of your time, because when go to the Asian, your solution should grow, but your solution is bounded when you go Asian. So means your solution should not depend on your time. Now, if a solution does not depend on time, then it's only a solution to the infinite problem. And so that's why you only have 6 solutions, from minus infinity to 0. So for the model problem, why we use H decay inside? Oh, this is a very interesting, very good question. Why? And the reason is when you compute the initial error, and you see your initial error is this form. Is tau to the minus, is you have time decay, some time decay, and you have some spatial decay. And so, and of course you assume that, and later on you use a fixed point. So you show that all your remaining part, including nonlinear term, are also in this Barkha space. And yeah.
Are you satisfied by this answer? I hope. Что такое? Cannot understand what microphone works. Почему такой? Почему так два раза? Cannot understand. So please, yet questions whether we have.
Only a comment from Lev Yegorov.
Yeah.
He thanks the speaker for the interesting talk. The question is as follows. For model problem, why we use H decaying in such a specific way?
I already answered, but let me answer again. And the H, because when you compute the first error, you plug in the first initial condition inside, you will compute the first error. Your first error looks like this form. And so you take this as your space. So your space, your error is in this place.
I'm sorry for asking the same question twice.
Yeah.
So if there are no more questions, dear listeners, do you see the option to raise your hand? Okay. If there are no more questions, then thank you very much again. We are waiting for your second lecture tomorrow very much. And
Thank you.
Thank you for today.
No, please don't forget to send us your presentation, please. No, after
Sure.
the second lecture. Yes.
Yeah.
Thank you.
Yeah.
Маркус, пиши.
Мы его озвучили, оказалось, что уже ответ.
Да.
Второй уже озвучен. So
we have
10 minutes.
Yeah,
we still have 10 minutes.
Break.
Mm-hmm.